You know those incredibly thin, super precise coatings you find on everything from your smartphone screen to high-tech sunglasses? Ever wonder how they get there? Well, it's not paint, and it's not some kind of plating. We're talking about building things, literally, one single atom at a time. And the process behind it is called sputtering. So that begs the question, right? How in the world do you paint with atoms? I mean, it sounds like something straight out of science fiction, but it's a very real technology that, honestly, our modern world couldn't exist without. The answer is this fascinating process that's part physics, part engineering, and just a whole lot of cool science.
Okay, at its core, the best way to think about sputtering is like a high-stakes game of atomic billiards. Seriously, imagine you've got your cue ball. That's a high-energy ion, and you're using it to precisely knock other atoms off of a material. Then those atoms fly off and land on another surface, building up this perfect, ultra-thin film. It's a game of cosmic pool, played on an atomic scale. Now, to even start this game, you're gonna need a cue ball, right? The particle that does all the work. And to get that, we first have to create a very special, supercharged state of matter. And that fuel is plasma. You've probably heard of it as the fourth state of matter. It is absolutely essential for sputtering because it's where we get the high-energy ions we need, our atomic cue balls. Without plasma, our game of billiards just doesn't even get started.
So how do we make it? Well, the recipe is actually surprisingly simple. You start with a really stable, inert gas. Argon is a popular choice. Then you hit it with a strong electric field. That jolt of energy is enough to literally strip the electrons away from the argon atoms. What you're left with is a soup of positively charged ions and free-floating electrons. And that, my friends, is plasma. All right, now we have our plasma, and it's full of those charged ions we need. It is time for the main event. In our game of atomic billiards, this is the break shot, that powerful, high-speed collision that sets everything else in motion. So what we do is we take those ions from the plasma and we use another electric field to accelerate them to incredible speeds. We aim them right at our source material, which we call the target. When these super fast ions slam into that target, bam! They transfer all that energy and momentum and physically knock atoms loose from the surface. And this brings us to a really important idea, sputter yield. This is basically how we keep score in our atomic game. It's the average number of atoms we manage to knock off the target for every single ion that we fire at it. So a higher sputter yield means we're being more efficient. We're getting more atoms for our buck, so to speak. And as you can see here, we have total control over that yield. The amount of energy we give our ions makes a huge difference. If we use low energy ions, it's kind of like a gentle tap. Yeah, you'll dislodge a few atoms, but the whole process is pretty slow. But if you crank up the energy, it becomes a powerful strike that ejects way more atoms, giving us that higher sputter yield and a much, much faster coating process. So we've successfully knocked all these atoms off the target, but where do they go? Let's get to the final stage of the process, where we see how we pocket these atomic balls to build something completely new. Those atoms that we just ejected travel through the vacuum chamber, and they land on another surface, which we call the substrate. The substrate is basically the canvas for our atomic painting. As more and more atoms land and stick, they build up, layer by perfect layer, forming a brand new, perfectly uniform, and incredibly thin film. And get this, the atoms don't just land in a random, messy pile. Oh no. Depending on the conditions we set, we can actually guide them to arrange themselves in very specific patterns. We can get them to form perfect one-atom-thick layers, or to clump together in tiny, uniform islands. It just shows you how incredibly precise this whole construction process can be. Now, this whole thing might sound a little chaotic, right? Atoms flying everywhere, but it is anything but. The real power of sputtering is the incredible level of control engineers have over every single step. It's all about having the perfect recipe. And this quote just hits the nail on the head. By carefully controlling things like voltage and gas pressure, scientists can completely tailor the final film's properties. They can change its texture, its density, even its internal atomic structure, all with just a few tweaks to the machine. This table here lays out the main control levers we can pull. If we change the voltage, we're changing the ion's energy, which, as we saw, affects the speed and density of the coating. If we tweak the gas pressure, that changes the plasma itself and how easily the ejected atoms travel, which impacts the film's quality. Even the type of gas we use has a huge effect on efficiency. But things get really interesting when we start adding a reactive gas into the mix. For example, just look at this chart. It shows the sputter yield for a few different gases. You can see right away that argon, which is a common choice, is way more efficient at knocking atoms loose than gases like nitrogen or xenon. So choosing the right gas is a critical first step if you want an efficient process. And this is where sputtering becomes a kind of atomic chemistry set. Instead of just moving atoms from one place to another, we can create entirely new materials during the process. By sputtering a titanium target but adding a little bit of oxygen gas into the chamber, the titanium and oxygen atoms combine right there on the substrate to form titanium oxide. This is exactly how we create things like those ultra-tough scratch-resistant coatings on fancy watches, or biocompatible layers on medical implants. So, we've gone from playing billiards with atoms to literally inventing new materials on the fly. Sputtering gives us this incredible fundamental control over matter. It's a technology that is already all around us, in our pockets and on our faces. So the only real question left is, now that we have this incredible power to build the world atom by atom, what challenges are we going to solve next?